I would like to present our next speaker, Rubén Vigara from University of Zaragoza, with a talk on filling dense surfaces in three-dimensional manifold. You are welcome.
Okay. Thank you very much. And first of all, I want to thank the organizer for giving me the opportunity to participate in this online congress in no theory in honor of Louis Kaufman. It's for me an honor to give a talk at this event. So let's start with a few definitions and remarks. What are filling dense surfaces in three manifolds? First of all, what do we understand by surfaces and three manifolds? They will always be considered compact and without boundary. Three manifolds are always connected, of course, but surfaces could be non-connected, okay? And also, we will consider always the orientable case. All surfaces and three manifolds are orientable, okay? So, what is a dense surface? Okay, a dense surface is the image in a three manifold of an immersion in general position. Okay, so imagine that M is a three manifold. So a subset sigma in M is a dense surface if there exists a surface and an immersion into the three manifold such that F of S is sigma, and sigma has only transverse singularities. That is, if we look at sigma, we can only see just regular points where there is also one sheet of the surface, or double points where two sheets of the surface intersect, or triple points where three sheets of the surface intersect. Okay, triple points are always isolated, and double points are arranged along double curves that could intersect in the triple points. Okay. So, due to our original hypothesis, there are some remarks to do. Since the surface is considered compact and without boundary, all double curves must be closed. Okay, if we start to walk along a double curve, we must end up in the same starting point. Okay. Also, since both manifolds, the surface and the three manifolds, are considered orientable, the inverse image of each double curve, note that if we consider one double curve in the original surface S, we can see over the double points, we can see locally two curves. So these two curves flows into two different curves in the surface, okay? So the inverse image of double curves is the union of two curves. In the original, the domain surface. And we say that these two curves are sister curves. Okay, we will give one name for the set of triple points of the filling Dehn surface. So Dehn surface, sorry, triple points. That will be always a finite set because of the compacity again. Okay. If this domain surface is of a special kind, the Dehn surface will have also a name. So if S is a two-sphere, for example, we say that sigma is a Dehn sphere. If it's a torus, it will be a Dehn torus. A genus G surface, a Dehn genus G surface, and so on. Let me show some examples. For example, a simple example here. We have one sphere that intersects itself, a couple of spheres intersecting along a double curve, a triple of spheres intersecting in pairs in double curves, and the three spheres in two triple points. Another surface with non-connected domain, for example, this one. Right. Okay. And when we consider in the surface the inverse image of the double curves, so for example, here in this example, we say that there is only one double curve here. If we look at the inverse image of this double curve in the domain surface that is a two-sphere, okay, we see a couple of curves that become identified by the immersion. So this picture is what we call the Johansson diagram of the surface. Okay, that is the inverse image of the singularities together with the identification information. For example, for this example that has not connected domain, the domain of this immersion should be the union of a sphere and a torus. And we can see here two double curves. There is one double curves around the torus, whose inverse image should be this pair of double curves here. We see another double curve here that correspond to this one and this one in the domain surface, and a third double curve behind that correspond to this one. Okay, the Johansson diagram is also called in some papers, for example, by Carter and collaborators, is what is called the double-decker set. Double and triple. Okay. Well, these are dense surfaces. So what do we mean by filling dense surfaces? Suppose that sigma is a dense surface in the three-manifold M. We say that it fills M if it defines a cell decomposition of the three-manifold where, sorry for my bad writing, there is small lag here, where the zero skeleton is the set of triple points. The one skeleton is the set of singularities, such as the union of the double curves. And the two skeleton is the surface sigma itself. So for sigma to fill the three-manifold is equivalent to say that if we take M and remove sigma, we obtain an union of three balls. If we take sigma and remove the double curves, we obtain a union of open disks. And if we take the double curves and we remove the triple points, we obtain a union of arcs. Well, for example, in the examples above, we see, for example, that this pair of spheres verify the first condition. The complement of the surface is a union of three balls, and the second one also. If we remove the singular set, the double curves from the surface, we obtain a union of disks, but there are no triple points. So there is no ferroskeleton in this cell decomposition. So this example is not filling. On the other hand, this one is a filling example because it is easy to see that it verifies all the conditions. Okay, so our interest in filling dense surfaces is because of the following theorem by Montesinos. That says that every three-manifold has a filling dense sphere. introduces this theorem based on previous works by Haken and Fenn and Rourke. And later, we could see that this Philin-Dehn sphere can be chosen to be null homotopic. Which is interesting for the next results. Okay. Well, so we, as a proof, we can see if we consider an schematic proof any three manifold, we can fill this three manifold with many embedded balls. And after that, we can connect these balls in pairs in such a way that we start to connect different spheres until we obtain a unique sphere that is immersed and verify the condition. It is a Philin-Dehn sphere. So when we have a Philin-Dehn sphere, if sigma, let's say it's a Philin-Dehn let's denote by this a Philin-Dehn sphere of then we can build the three manifold from the Johansson diagram of the sphere. Okay, we can recover M from so we can represent all three manifolds by diagrams of null homotopic Philin-Dehn spheres. Okay. So some results that came after this original result from Montesinos. Some time after this, we obtained a set of moves for Philin-Dehn spheres. Okay, imagine that we have a Philin immersion of a three manifold, another Philin immersion on another three manifold that are null homotopic. Null, that is, they are homotopic to a constant map. Philin then the two three manifolds, they refill the same three manifold if and only if we can deform F into G by a sequence of Philin immersion that are related by a set of moves that I will show you now. These are the set of moves or their inverses. Okay. Later, this set of moves were improved a little bit by Amendola, Genaro, that gives an equivalent set of moves. And using his set of moves, introduces a state zoom invariant for three manifolds from dulomotopic filling dense spheres. More results. In 2003, Roger Fenn, during the Congress not in Poland, asked me the following question. Do they lift to embeddings in m times the interval? So the answer is that sometimes they do and sometimes they don't. So we have the following theorem inspired by Fenn's question. Theorem. Every three manifold has liftable and non-liftable filling dense spheres. As liftable and non-filling dense spheres. So we know that filling dense spheres is the image of an immersion into the three manifold. They lift if we can obtain a lift to m cross interval such that this is an embedding. Okay, on one hand, the filling dense spheres that come from previous proofs of the Montesinos theorem, for example, the original spheres introduced by Montesinos from Hegar splittings are liftable. It can be seen that they lift to embeddings. Previous. How can we know if an immersion lifts to an embedding? There is a previous work by theorem by Giller that are for spheres immersed in R3 that he looked for which of them are projections of two knots in R4 that says when can we check, how can we check if these immersions lift? And this Giller's theorem, it can be extended to this case. So Giller gives us a criterion and also gives an example of an immersed sphere in R3 that do not lift to an embedding in R4 in S3. The criterion and the example can be seen also in papers by Carter and Saito. The sphere, Giller's sphere is the double cover, the surface that runs parallel to the voice surface, which is a projective plane in R3 with one tripole point. So the parallel surface is a two sphere with 8 tripole points and is filling. So Giller's sphere is filling. And if we have a general three manifold, and we take inside it any filling Dehn sphere in the three manifold, since the complementary set is a union of three balls, we can put a Giller sphere here inside, Giller's example, and we prove that we can connect these two surfaces in such a way that we obtain a filling Dehn sphere of the three manifold that do not lift due to the presence of this Giller part. Okay. On the other hand, we have tried to understand some properties of three manifold that can be seen in filling Dehn surfaces. We have trying to study the simplest examples. So simplest filling Dehn surfaces give us a measure of the complexity of the three manifold. Sorry. So let's define the following number given a genus G that can be 0, 1, 2, etc. We define tau G of M as the minimal number of triple points of a genus G filling Dehn surface. Okay, number of triple points. When we talk about filling Dehn spheres, we call this Montesinos complexity. So for each genus, we consider all the genus G filling the surface of the three manifold, and the minimum number of triple points is this number. Okay, how can we obtain information of the three manifolds from these numbers? How is this measure of complexity? We have, for the Montesinos complexity, we have a theorem that it is subadditive under connected sum. If we have two three manifolds and we have their connected sum, the Montesinos complexity of the connected sum is lower or equal to the sum of the complexities of the three manifolds plus 2. And we cannot remove this 2. This inequality is sharp. On the other hand, for a given three manifold, if we consider the full sequence of triple point numbers, we obtain what we call the triple point spectrum. there is one easy result. Let's say theorem. Although this is not a difficult one. Now g plus 1 of m is lower or equal to tau g of m plus 2. And if we have the strict inequality, implies that the number of exterior regions is reduced. The number is where this inequality comes from the following construction. If we have a cylinder surface of genus G, we can obtain by a small modification, adding 100 of this kind, we obtain a filling-dense surface of 1, where the genus is increased by 1, but we have 2 more triple points. So if this surface is a minimal genus G filling-dense surface, we obtain a filling-dense surface with 1 more genus with 2 more triple points. So because of this, we have this. And we can see that when we make this operation, the number of connected components of the complement do not change. So this number of connected complements is related to the number of triple points and the Euler characteristic of the surface. So this implies that this result, that the number of 3 balls, if we obtain, if there is a filling-dense surface of genus G plus 1 such that the inequality is strict, the number of 3 balls in the complement is reduced. This implies, because the number of 3 balls in the complement cannot be reduced an infinite, there is a finite number of 3 balls. This implies that the spectrum of triple points of the 3 manifold always stabilizes. There is one genus such that the next ones always are obtained adding 2 and 2 and 2 and 2 and so on. So excuse me, because my computer is so slow. It's going so. We have proved that we have found the simplest triple point spectrums. We have proved this is, sorry, that the triple point spectrum of S2 S2 crosses 1 is the smaller possible one, 2, 1, 3, 5, etc. And we could prove that the triple point spectrum of the 3 sphere is 2, 4, 6, 8. We have some examples of filling dense spheres of the free sphere with 2 triple points. These are the simplest ones. So we can construct filling dense torus with 4 triple points and so on. The question is if there is a filling dense torus in the free sphere with less than 4 triple points. We prove that this cannot be possible, and also for the other genus G surfaces. So this is the spectrum for the free sphere. This is based on the following theorem, that if M is a C2 homology sphere, the triple point number of genus G is lower or equal that 2 plus 2G. Okay. Now, after that, we found some applications from filling dense surfaces to knots. We say, imagine that sigma in a three-manifold is a filling then a surface, not really and it is not necessary a sphere. Consider a link or a knot in the three-manifold. We say that sigma splits L if and only if the idea is that the link each face of the dense surface, if we look at a face of the dense surface, can contain at most one intersection with the link. And each region of the dense surface, each complementary ball of the dense surface can contain at most one arc of the link, and that is a knot. Okay. Excuse me. Something's happening with my notebook. Let me try with another software. Okay. So, sorry. Then we prove the following theorem. For each link in any three-manifold, we can obtain a filling dense sphere that splits the link. for or there exists a filling Dehn sphere that splits. So we can recover the three manifold and the link from the Johansson diagram of this splitting. So for example, we can see that this is a filling Dehn sphere in S3 that splits the trefoil knot that we can see in some way here. And the Johansson diagram of this sphere with the intersection of the knot marked is this diagram. So we can recover the three-dimensional picture from the diagram. Here is the red stars are the intersection of the knot. So we can do this for any link or knot in any three manifold. This is very useful for for studying branch coverings along the knot or the link, because we can construct the Johansson diagram of these branch coverings from the original Johansson diagram of the splitting surface. For example, we can obtain the Johansson diagram of the branched covers of over the trefoil, starting from this one. Okay. This is especially easy in the case of the cyclic coverings. So I think my time is over. Sorry, because of technical reason, my computer is so slow today. And
You
so
have a couple of minutes.
A couple of one. So I can tell you a little bit of what are we working now on. No, I think I will stop here. So thank you very much, and happy birthday to Luke Hoffman of his 80th birthday.
Thank you.
I'll finish here.